Our next presenter is Melissa Suma, who is a master's student at the Department of Laboratory Medicine and Pathobiology, with her talk titled On the Beat, a safety mechanism for heart cell therapies.
In Canada alone, 750,000 people are living with heart failure. That means 1 in 3 of us in this room today has or will be affected by this disease. As of September, the national heart transplant waiting list consisted of 3,500 people. Stem cell-derived heart cells are a new potential therapy for heart failure, one that can regenerate new muscle rather than just treating the symptoms of this disease, and one that can help to offset some of this demand for full organ transplants. These cells are especially unique for their ability to become heart cells in a dish, ready for transplant. However, there are several hurdles that we need to overcome to make this therapy viable for the human patients who need it. One of those key hurdles is called arrhythmogenesis. In each of your healthy hearts, each of your muscle cells beats in a precisely timed manner with its neighbor, like the members of an orchestra all playing in sync. This results in a reliable heartbeat that pumps blood throughout your body and keeps you alive. In heart failure, many of these processes are damaged, and the heart can't pump blood as well as it needs to. Stem cell-derived heart cells can form new muscle and link up with the surrounding tissue to restore normal heart function. However, these cells can go through a transition period when they're first transplanted, where they can start to beat to their own rhythm. You can think of this like the new member who just joined the band. He's really enthusiastic, but he just hasn't figured out how to sync up with the group yet. And this can cause an irregular heartbeat, known as an arrhythmia. This is what my project hopes to solve. We're trying to create a safety mechanism inside of the transplanted cells, one that could turn them off if they start to cause arrhythmias. We do this by editing the genes or the instruction book of our cells so that they make this safety switch. And this safety switch responds to a specific drug. As you can imagine, patients in future could be monitored closely after their transplant, moving from the left to the right, and if they start to show signs of an arrhythmia, be given the drug to turn the graft off. The drug affects the graft because only it has the safety switch, and over time, it could mature inside the body and start to beat to the rhythm of the patient's heart. We've made exciting progress so far, showing that our safety switch works in the dish, and we're hoping to fine-tune this response and then test it in an animal model of transplantation. Our ultimate goal is to make the transplantation of stem cell-derived heart cells safer, bringing us one step closer to a true regenerative therapy to give these patients a second chance at living a full life. Thank you.